Hi everyone. Welcome to another episode of Robo Papers. Super glad to have Harold with us today. He will be presenting his work at and his team at Comma AI. It's the paper is called "Learning to Drive from a World Model." Welcome to the pod, Harold.
Thank you. Thank you.
Yeah. Maybe as a start, if you could share a little bit about yourself. I read on your tweet that you've been working on this problem basically for 7 or 8 years. So yeah, could you walk us through your journey a little bit and maybe the motivation to this paper?
Yeah, sure. So I lead the autonomy team at Comma, and Comma's been around for almost 10 years now, and we've always been kind of founded on this idea of learning methods that scale well with compute and scale well with data are kind of the best long-term strategy to solve any robotics problem, and also kind of a really interesting thing to work on in this kind of future where we switch to more and more things being automated. Self-driving, I think, is a really exciting problem to try a lot of these methods on because partial autonomy is useful. People are willing to pay money for it, so it means you can make products in the meantime. And so we've kind of been starting from that, working on that since the beginning. But the goal has always been to make end-to-end methods that just look at data and then kind of figure out how to do stuff. It's easier in self-driving because there's expert demonstrations that's very easy to collect. We sell a device and that collects a lot of data. And so over those past 8 years, we've kind of been building simulators so that we can train in simulation on policy, kind of made the bet early on that on policy training is kind of the only thing that works, but on policy training and simulation is fine, so you don't have to do it in the real world. And then, basically all of that work kind of culminated into this first paper where we describe the method we've built to train in simulation on policy that works. It's shipped to real people. It's what runs in OpenPilot. People use it. It's useful. And the paper kind of describes our first method of doing that and also describes our latest method, which uses a world model as a simulator. And that's what we're actively working on. We haven't really fully gotten all of the benefits out of that yet. The paper is kind of the first success in that it has not made it to release yet. There are still things to work out, but we expect that as soon as we really fix some more of these issues, we expect performance to increase dramatically in the field.
One thing that I feel like is really cool about Comma, like I was in self-driving cars back in 2018, 2017, around then too, and I feel like it looks very, I've always admired that you guys you were end-to-end believers at the very beginning and have like stuck to your guns and have like now look very prescient, I think, right? Because everyone is going in that direction.
Yeah, it's cool to see the bets kind of play out. In the beginning, it felt like a crazy, I mean, I didn't think it was crazy, but it felt controversial to some people. But now it's cool to see that everyone agrees this is a good strategy. It's just a matter of getting it to work and shipping it. But I mean, the proof is there. We do actually ship a product that people use, and it truly does not depend on really any hand-coded stuff, at least when it comes to lateral in what we've shipped. And it's reliable. It reliably stays between lane lines, despite the fact that it's never told to do anything like that.
Yeah, so maybe even before we dive into the papers, and for those who don't actually know too much about Comma, I think it would be helpful if you can maybe share screen and show the actual product, right? You mentioned it's easy to like collect data for driving, but I think what you guys have done like just on the data collection part is non-trivial. So I think, yeah. In fact, today I just sat in someone's car and actually he has one of the Commas, so really cool.
Sure, yeah. I mean, I can just, this is our website. We sell this device that you install in your car, and basically on a few hundred different car models like Kias, Hyundais, Toyotas, Lexus, it can give you better ADAS features than the car ships with. We can, connect into the CAN bus where we can control gas, brake, and steering the same way that the car manufacturers do with their modules. It's just we replaced their stupid modules with a new device that uses some actual modern machine learning to give you some decent autonomy. And I mean, you can see plenty of videos of it driving. If I just pick on some random, I mean, it's like highway autonomy mostly, does some stuff in the city, but over our entire fleet we have around, let me show you this video. We have 52% miles engaged on average right now. Share something else. And this is just the first video I clicked on from a user. But yeah, we have a little over 50% of miles driven of people that buy our product are driven by OpenPilot. So it gives you kind of an idea of how much people use it.
I'm curious, I imagine it's a non-trivial thing to have one single device that plug into so many different car make. Have there been hardware standards that they have formed around these different car makes so that allows you to do that? Or is that
so? Yeah, there's definitely no standardization whatsoever. It is a pretty difficult project to reverse engineer all the APIs that these cars have. The community helps in this. We don't port most of the cars anymore that get added to the fleet. The community usually starts. Sometimes we help out. But yeah, there is no standardization whatsoever. The only standardization is basically the CAN network. But what messages you actually have to send to do stuff needs to be basically reverse engineered for every brand, especially, and then usually for groups within that brand as well.
Yeah, but
For
I
the
think
models, you don't see any specialization. Sorry. Like, do you think the mixture, do you have to do anything to handle like the mixture of different car models that you see or anything like that?
Well, we need to make the models robust to various problems with controls, which is definitely not trivial, but it's also something that makes the models in general just more robust. Whereas we might struggle with dealing with some cars that have laggy steering, some cars that have steering that is, sometimes steers too much, sometimes steers too much in some situations. If we were only supporting one car that was actually very responsive, we wouldn't have to deal with that problem. However, that also translates to dealing with all sorts of noise and all sorts of problems that pop up anyway, like wind or road bumps or that sort of stuff. So it does require our models to be more robust than probably other people would have to make them if they were just supporting one car. But I think overall it makes a more robust machine learning product.
Yeah, I think it's great that now that you guys have managed to get so many types of cars like that support that the variety of the data set, right? It's not just one car. Yeah, so I guess okay, maybe this is a good segue, like from the data set to talk about the actual paper, because
Sounds good.
everything is learning based. And you mentioned this. Is this a first paper from you guys, or?
We've published very small stuff. We've published a data set, but I'd say this is our first interesting paper.
Interesting, because I mean, you guys open source basically everything, right? And but why do you feel that this require a paper?
We open source as much as we can, but when it comes to the models, we publish some blog posts, we publish data sets, but how the models are trained and how they actually work, that even though the models are published, that's not really something people have insight to. And we like talking about it. We're very transparent about it. But the paper is a good way to really explain what's happening because it's not that trivial.
Got it. Cool. Yeah.
So yeah, I can. I'm not sure if we want to talk about any part in particular in the paper, or we can kind of try to give an overview of basically what it's about.
I think, yeah, it'd be great if you can give us an overview, and then we can start asking questions, and then we can jump around the paper.
Sure. I mean, so the core of the paper and what we've just been working on is how do we take expert demonstrations from the driving data and distill that into a model that can drive. We have some baseline assumption that you can't just do off-policy learning on the expert demonstrations, because what you'll get is something that in the real world is not robust to any kind of noise, which means that even just the imperfect controls and wind and things like steering alignment will introduce noise, and you'll slowly start drifting out of lane, for example. And so you basically get a system that doesn't drive at all. And, empirically, we've tested this. Other labs have tested this. If you train something completely off policy, it largely doesn't work. So that's one of the big assumptions that we're making. So given that assumption, we have to train on policy. On policy can mean on policy in the real world or on policy in simulation. Obviously, on policy in simulation is much cheaper. On policy in the real world means, having your model experiment in the real world on real cars. That's expensive.
Yeah, you can real world crushes.
Yes, exactly. Yeah, might also be dangerous, but it's for sure expensive.
Yeah.
So, we need to train on policy in simulation. And, you can make some kind of classical simulator, which is something that people do in robotics. You can make some physics simulator. A lot of humanoid robots now learn with classical simulators like Mujoku, and they kind of learn how to walk in with some basic physics model. But the problem is that it's very hard to capture any kind of nuance in driving with a classical simulator, because how do you simulate, a drunk person that's stumbling over the road, or a goose, or a deer? You can explicitly only do so many things before you start to kind of, waste your time and get some method that doesn't really scale. So we want some kind of data-driven simulator. The paper describes two different simulation strategies, one which we've basically been shipping for years as an end-to-end strategy, and the other one, which is the new world model one. I can show you here we talk about these two different simulation strategies, and not sure how well this is really captured. It's kind of hard to see, but so one way to simulate stuff is just to take real data, and then you can kind of move the image around. You can do some depth map, and then you can reproject things and pretend like you were in a different location. And if you do that, you can make a simulator where you can deviate from the data collected in the real world slightly. In our case, we can deviate a few meters left, right, forward and back. And so we can train on policy and let the model make some amount of mistakes, and then show it a recovery. So that's simulation method one. And then in the paper, we also talk about the alternative, which is explicitly predicting with a machine learning model different trajectories that are grounded in real data by providing real context. Yeah, maybe let's talk about this for a bit before I go too deep off. Some stuff here is quite difficult to understand if I keep talking.
Yeah. Sure. So this particular one is what you have for years before this world model, right? Before this paper.
Yes. So this simulation strategy of doing reprojective simulation. So in the past, they used to not even do depth estimates. They used to have like really simple assumptions about the scene. For example, that everything is either a car, background or the ground, and you can assume that the road is flat and stuff like that. But recently, we do some level of depth reprojection, which gives us a little bit more detail. And then we do some tricks with the hood so that that's reprojected correctly and stuff like that. But yeah, that's what we've been doing for years. That's how we managed to ship like a full end-to-end lateral driving stack that does not use lane lines at all anywhere in the control policy. And then in this paper, we describe the new method of using the world model. The paper also describes a ground truthing method for recovery trajectories that can be used in both the world model simulator and the reprojective simulator as well. There's kind of two parts. One part is you have to be able to simulate, mistakes and deviations in your own policy trainer. The other is you also need to know what a reasonable recovery is.
Sorry, if I can just double take back on the original method of the reprojection, right? So you did mention somewhere in your paper that there are various limitations. Something about you're assuming the whole thing is a static scene, occlusions and all that. Could you talk us through a little bit and how may your new world model actually solve some of these?
Yes. So I've got the limitations here. So one problem is we assume the scene is static and that our deviations cannot affect the scene. So if you swerve towards a car in the real world, that car might react by swerving away from you or driving faster or slower or something like that. But in this reprojective simulation, we have to make the assumption that, the scene does not react to our actions. So that's one limitation. That ends up not being that big right now. This is kind of more nuanced. Another problem is just that the depth maps it's kind of hard to get good depth maps. It's also not clear what depth means in some cases. When you have reflections of a street light in a puddle on the road, what is the depth of those lighting effects? There's no answer to that. So that creates kind of artifacts in the reprojection that make the image look unnatural. Obviously, occlusions, there's nothing to do except in painting, which sometimes is a problem. And then all of these artifacts get way worse the more you deviate from this original ground truth data. And the biggest problem with all these artifacts is the artifacts themselves may not be that big of a problem if they were completely uncorrelated with anything. But they are correlated with the deviation from the original trajectory, which means if you have a model training in that simulator, it can extract the original driving trajectory from the artifacts if the artifacts are bad enough. And given that that's our ground truth for what is a good driving trajectory, because our assumption is that the human driving trajectory, was desirable, that means the models effectively cheat. They see these artifacts, they derive where the car originally was, and so they learning the artifacts instead of learning the actual driving policy of you shouldn't be close to a barrier or a parked car or stuff like that.
Got it. So it seems like everything is set up for world model being a better approach. But what took you guys took quite a while before you start exploring? Is it because you just need more data, or is it some other innovations that need to happen before you guys start actually experimenting with world models?
So I haven't addressed a big part of this paper yet either, which is the how we give ground truth for what is a desirable trajectory. In the reprojective simulator, what we did until recently is we knew where the human trajectory was, and we used, traditional planning and control, which is MPC, to say, find some smooth way to get from where you are back to that human trajectory that we know is, fine. And that's like pretty straightforward. However, once we really start thinking about world models and simulations that can deviate from the original context, we can't do that anymore, because let's say you deviate to the right in some simulation. Like if we take this case, for example, you're just driving and then you deviate strongly to the right, the world model may imagine a pothole, which would make the scene more consistent of why we deviated to the right. Now, if we would use the original ground truthing method of, you should try with MPC to get as back to the center of the lane as soon as possible. Now this conflicts with the inputs of what the model's seeing, because it's now imagined this pothole that wasn't there in the original data. So we need to find some way to provide some driving policy ground truth that recovers from deviations, but is also consistent with what the world model is imagining. And so the way we do this in this paper and what we've been working on is, see if there's a graph here that makes this clear. I mean, maybe this is the most clear graph, is we anchor the simulation not only to an original context of real data, but also to a future of real data. So let's say we have 3 seconds of context, we have 3 seconds of future that we're anchoring to, and then we have, let's say, 10 seconds in between of actual simulation. All we're asking then, we can ask the world model then is, not only what is the next probable frame given this existing context and this future anchoring, but also what is a reasonable way to get back to that future anchoring. So then we can essentially have the model directly predict recovery trajectories without needing to use MPC or any kind of classical control. And that innovation was kind of a big breakthrough in what allowed us to, think about using world models.
I see. So it actually not so-called a lack of like data set size. It's just like actually the formulation of how you get the ground truth.
Yes, I mean, but of course, a couple years ago, we didn't have the compute to meaningfully train any kind of world models. I would say data set is much less been a problem than compute.
Got it. Yeah, because I think you train a few models and the largest one was like 400,000 minutes or something like that. That's like 7,000 hours, right? I think is something like that.
Yes, and I mean, we haven't been putting that much effort into collecting more data. I mean, we have 10,000 users on average driving probably 30 minutes to an hour a day. Like there is plenty of data available. We haven't put that much effort into it. It's not been a bottleneck. Now with the world models, they scale with data much better. So we're putting more effort into this. But in the past, that's not been a huge bottleneck.
Cool. Yeah, so maybe you can get back to the whole setup of world model again. So besides the ground truth, that's like the second part of the world model.
Yeah, maybe this original plot here is probably the most the most explanatory. I can just walk through this and see if we're all on the same page. So basically, we have some context of real data, which is of course important if we want to capture the full diversity. And then we can have some policy that predicts some action, which in our case is curvature and acceleration. And then we can tell the world model, given this curvature and acceleration that's been commanded, what is the next most likely image. And so then we predict another image, and then, we can kind of roll out the simulation like that. And the world model always gets in this future anchoring context, which is just a bunch of images at some point in the future. That kind of constrains it. And that also allows us to ask the world model not only what is the next most likely frame, but what is the most likely trajectory, like in 3D space, in meters, to get from wherever you are now in the simulation back to that future that the human ended up in. And that's what gives recovery. So that means that during a simulation, if we introduce noise, that recovery trajectory from the world model will always kind of bring you back to the desirable human trajectory. I think maybe I can show this in the meantime on this on the blog post, because that's the kind of most clear way of showing this.
Yeah, this is a really interesting paper. I'm trying to wrap my head around what role the world model's actually like playing here still, because I feel like it feels like like you're training it on the same data that you have access to as far as supervised. I guess is the issue that the data that you get isn't good enough from your users, or is it like why do I basically what role is the I don't know, this isn't a very well posed question. I'm sorry.
But are you saying that?
Right.
I mean, we can train off policy on the data with the human demonstrations.
Right.
But I mean, that is kind of our core assumptions. I can try to explain, I guess, intuitively why I think that's can never work. But yeah, so just in case this demonstration helps of what the world model does here, you can kind of see how you can deviate during the simulation, and then the world model predicts this recovery trajectory. Yeah, so I mean, we're talking about that's what you're asking, right? Why can't we just train off policy on the entire data?
Yeah, exactly. Yes, like that would be like the first guess would be that you could just try to train off policy. So I'm wondering why that doesn't work. Yeah.
Just imagine you're on an infinitely long highway, and the human is 50 centimeters off the center of the lane, and then the off policy question is, what is the most likely thing for the person to do in this case? Now, if you look at any data like that, you'll see that the human is gonna, for the next few seconds, drive straight. So that means not recover from this kind of deviated state that's not ideal. And so if you train a model that predicts what is the most likely thing a human can do here, it's gonna say drive straight. So your model will drive straight, your policy will not recover, and in 10 seconds or in 50 milliseconds, you ask the same question again, and it's again going to say drive straight. So it's pretty easy to see how, at least in that case, you're never going to recover from the fact that on this infinitely long, empty highway, it's not going to have really any pressure to converge to the center of the lane. And then you add to that especially because we support so many cars that have all kind of different and weird controls, when we say go straight, the car doesn't go straight. There is some non-trivial amount of noise that is introduced both from wind and road noise and that sort of stuff, but also from the fact that our control just isn't that perfect. So what you get in practice is something that just drifts out of the lane very quickly because there is no pressure to recover from mistakes, added to the fact that there is just perpetual noise being introduced.
Yeah. I would think that you would have like humans recovering, like a human driving is a visual motor policy, right?
Yeah.
Like maybe not even fundamentally all that different from what your algorithm is learning. You could even argue, right? Like so, like there are corrections that we are learned that in this data set, if I'm drifting over to the right too far or something. But I think I see the point though. Like this at least lets you leverage that. I can see how this would let you leverage that data much more effectively. Like,
I think I can say some more things that make maybe more clear is for sure there is in our data set enough recovery trajectories that go from this deviated state to the center. But finding that would require a filtering algorithm that is likely, just as complicated as whatever it is we're doing, because we're trying to answer this question of which behaviors are recoveries. That I think is basically as hard of a question of what we're doing. But what the simulation allows us to do is to introduce noise and saying that correcting the noise is always the right thing to do, which is a reasonable thing to do. If I just randomly add noise to your driving, it's reasonable to say that whatever gets you back to before I did that is a good idea.
Yes, that makes a lot of sense. Thanks.
Yeah, so but I guess the way it's set up now, given that there's basically a future anchoring, which means you're assuming that this is a salvageable mistake, right?
Mm-hmm.
I was wondering if so does it mean that right now the world model that you set up in this paper, basically you can't just tell the model, hey, what if I just completely swerve to the left and I should bang and then the whole thing should be black color, right? That's the end of the simulation.
Yeah, I mean, I think that the way you put it is good. We were just assuming all mistakes were salvageable. As soon as you kind of go, I guess, off the map or whatever you want to call it, like the simulation's kind of just over.
I guess my bigger even question is it even possible to train a world model using basically, because I imagine nearly 100% of the data that's collected in the real world are, basically salvageable thing. But then maybe the most worth it to like the biggest I think like you mentioned, the biggest benefit of having something like a world model is that you can just simulate things, right? If there's a crash, that'll be the best, right? Like simulate all kinds of crashes.
Right.
But if it's not inside the training data, can you train a world model to give you that kind of, because that's the biggest benefit, right? Isn't it?
I mean, yeah, I think it's reasonable to say that without any crashes or without enough crashes being in the data set, you can't explicitly simulate driving directly into a wall. But I think it's not that relevant for us because almost all things like crashes require getting close to crashes, which is something that's plenty in the data set. There's, tens of thousands of cases in our data set of getting very close to something right before you crash. And I think it's a very clear continuum, and we don't need to simulate crashes to avoid crashes.
Got it. I see. Yeah. So long it doesn't crash, there is the future anchoring because it's salvageable ultimately. And then, okay, I see.
I mean, effectively what happens is because of the future anchoring, if you give it actions that put you in a simulated space that is incompatible with the future anchoring, you're kind of breaking the rollout. Like an assumption here that we're making is that the actions you're putting in have to be somewhat compatible with the future. Otherwise, you're giving inputs to the model that are just inconsistent.
Got it.
All right. Sorry, I have to run. This is really cool stuff.
Worries.
This is awesome.
Yeah.
Sorry.
Nice talking to you.
Yeah.
Yeah.
Bye.
See you, Chris. Yeah.
See ya.
Yeah. I think so. You guys build this world model. Like, how do you actually like evaluate like in the real world? You build an actual policy, right? To actually and then deploy in all this the devices.
So we're talking about evaluating the driving policy that's trained in the world model, or evaluating the world model itself?
No. Okay. Maybe let's talk about evaluating the world model first. Like how do you evaluate?
So I thought that this is quite clear. So this is basically our evaluation part of the world model. So one thing we can do is we can look at the LPIPS perception loss.
Yeah, could you explain what is LPIPS?
It just compares the vision features based on some like standard trained machine learning model of the original video images compared to the ones that have now been simulated by the world model. So because both the beginning and end is anchored, we can make some assumption that if the world model is working very well, that in like visual feature space, the simulated images should look similar to the original video. And so that's what this loss shows. And you can see that at frame 10, which is when it starts simulating and starting the simulation, the loss is very low. And then as it gets closer to the end of the rollout, because it's further away from both the context and the anchoring, the quality gets worse. And then as we get back again to the anchoring, the quality gets better again.
I see. But just to put a time to it, so 10 is like 2 seconds, is it? Like
Yeah, this is 5 FPS. Yeah. So in this case, there's 2 seconds of context, 1 second of anchoring, and then 7 seconds of simulation.
Got it. I see. So what this chart is showing is that eventually it will still come back to the last 1 second after 7 seconds.
Yes, like the images get a little bit closer to reality again. Yes.
I see.
And then we can do the same thing for all these models. Take in and output also motion. So 6 degrees of freedom, position, and orientation rates. And you can see we can plot those errors too. And it's a bit noisier, but you can kind of see a somewhat similar pattern. But the most interesting evaluation method is if we start a simulation, we can then give in actions that take you to the left. So in this case, we try to get to a 50 centimeter deviation, both the left and right, and then let the world model recover back to the anchoring at the end. And so if the world model is perfect, it should track exactly that 50 centimeter deviation. But the world model doesn't perfectly listen to what it's told. So it's somewhere, somewhere between not doing anything different and this desired 50 centimeters. And what we're seeing here is, so what we expect given the actions we commanded, and then the dotted lines are what we see in the image by measuring the distance from lane lines.
Got it. So this is literally like a top-down view of the car, and you say turn left, but then the actual world model may not turn as much as you want it to go, but then it will recover basically to the zero, like the center line, which is the future anchoring.
Yes. Yeah, that's exactly
it. Got it. Okay. Yeah. So this is how you, I guess, evaluate the world model. How do you evaluate the actual driving policy? Or how do you use it? In fact, use the world model. How do you even use this world model in practice? in the
So
driving
in
policy?
practice, how we use the world model is extremely similar to what this image shows, which is we introduce deviations. Now, in this case, the deviations are just, very explicit, move to the left 50 centimeters and move to the right. When we actually train, we have very complicated world models that do all sorts of deviations from the original trajectory. But in principle, it's this. So we introduce some deviations, and then we ask the world model what is a normal trajectory to get back, or a human-like trajectory to get back to that future, and then we teach the policy model to mimic that world model prediction. So this image is really very representative of how that works. It's just the noise models are much more nuanced than just go left and go right.
I see. So when you say you do this on policy and in simulation, that means in world model, you basically train the driving policy to learn how to basically get back to
Yes, exactly.
to the center lane. I see.
Exactly.
Got
Yes.
it. And
I mean, center lane is an example here, and this obviously it's end to end, so it doesn't depend on anything to do with lane lines.
sure. Yeah, it could be turn left, but then so long it go back to. I
Yeah,
see.
exactly. Just any deviation from the original trajectory.
I see. And so it sounds like because this is on policy because you kind of have full control on the environment and I guess the state and you can observe the action as well. So therefore you can actually let the RL do its thing.
Yes, I mean it's not RL in this case, but yes. But yes, the policy that we're training in this world model simulation, gets to act and is exposed to its own mistakes. And yes, we could do RL, but every time we try RL, it doesn't work.
Okay. Wait. So how is this policy? How is this being trained? You mentioned it's not RL.
Oh yeah, so it's just so the world model describes a trajectory, which in this case would be this trajectory. We just try to mimic that trajectory with like a negative log likelihood regression loss.
I guess. Okay, got it.
And then we just execute that trajectory as an action.
I see. Okay, so now you train hopefully a better driving policy, and how does it actually perform in the real world?
Yeah, so once we've done that, then we can I can show you some. So one of the beautiful things about end-to-end is your test suite doesn't need to be that comprehensive, because as long as you made good end-to-end training strategies, if any subset of the behaviors work as the way you want, you can have some expectation that the rest will work too, because you didn't do anything behaviorally specific during training. So if you're if you train, this model completely end to end, and you observe that it stays in the center of a lane on a normal simple road, if you did things correctly, you could expect that all the other behaviors are also learned relatively well. So we have a pretty simple test suite that we just run in many different ways. And here's one example: is just a turn on a super simple simulation where we just initialize the model in many different states and see does it converge to the same place in the lane every time. So if we train off policy, I don't think we have those plots, but when we train off policy, it would not do that. It would basically just stay wherever you initialized it. And then if you introduced noise, it would drift out of the lane entirely. So this kind of shows one desirable behavior is wherever you start the simulation, in a few seconds, it converges to the same place every time. So that's one test. Then we have some tests that, initiate lane changes. And I mean, we have, let's say, a few dozen of these types of tests, and then a few hundred metrics that we look at. Actually, if you're interested, I could show you those look like in detail too. Right here. Oh, I keep getting lost in the screen sharing.
No worries. Yeah, I can always cut this part out, so it will still look like a smooth podcast. No worries. Yeah.
But yeah, so this is a bit more detailed than the paper, but this is, we have all these kind of metrics that look at, what is the error in turns when we, run simulations, how is the speed prediction, and some of these tests are also on policy in different types of simulation. Some of them are in classical simulation, some of them are in these reprojective simulation. If we train in the world model simulator and test in the reprojective simulator, we can get a lot of ideas. And this is a test that shows left and right turns. Does it kind of always, is there any bias during turns to cut turns or something like that? So we just have all of these kind of different metrics that we run in various simulations. and that kind of gives us some idea of how the model will perform. And there's some more tests here. Yeah, we have all these kind of different recovery trajectories where we initialize in different simulations in different locations and see how quickly it converges to the center of the lane. We have the same for turns and different speeds and all this sort of stuff.
But you also test this actually just now on the paper. You have this small table where you have the engage percentage. Those are actual real. Could you explain like the engage percentage? Like what are these? Like how do you infer
Oh,
this?
sure. Yeah. So basically, that's our offline valuation strategies. That's how we decide whether we think something is good to actually drive on in the real world. We include this in the paper of what the performance in the field actually is, but that's not something that we would use to evaluate whether something good or not. I mean, that's not an efficient way to develop. This is just a kind of last point proof that it kind of worked. So we had the model that was trained with the world model in our master branch of OpenPilot for a few months. And so we just looked at the engagement data just to kind of prove that, this was something that was useful, that people were voluntarily using and was driving significant part of their commutes. So in this case, it's 52% of miles engaged for...
Could you explain a little bit like what is engaged by distance
sure.
and engaged by time?
I mean, OpenPilot can be either engaged or disengaged. Engaged means it's doing everything, gas, steering, and brake. And then disengage is you driving. There's kind of not really much in between. So this is just saying that for the average user that has the device installed and is running OpenPilot, 52% of their distance of driving in miles is driven with OpenPilot doing the gas, steering, and the brake. And the distance percentage is much higher than time because people are more likely to engage on the highway.
Got it. But even by time, it is still, it is still, I guess, a 2% bump, right? At least.
Yeah, but it's unclear if we can draw too many conclusions from this. I mean, I think at most we can say that it's comparable, as in it both works. There's kind of a small difference. I mean, there's only a few hundred users. Not sure we should draw too many conclusions from that.
Got it. Oh, I mean, it's 40,000, trips. It's, I think.
Yeah, it's not a trivial amount of data. But, there's also some effect of when we ship, a new exciting type of strategy, people are more inclined to try it. I just don't want to draw too many conclusions from this. I think it's fair to say that both strategies make a useful ADAS product that people want to use.
Yeah, I guess the biggest thing, maybe especially for autonomous like research, is like you can do a lot of things in color and then I guess like what's that, meta drive, like places like this simulation. But nothing beats just deploying in real world scenario. Let the humans tell you, whether they like it or not, right?
Yes. Yes, I think it's very easy to even unintentionally fool yourself that something is good or bad, but users, especially paying users, are, I think, brutally honest critics of how good something is. And I've also learned they're very difficult to fool.
Yeah, for sure. But I imagine like many of your, the community that actually, what would you say, like what, these folks who buy, the combo device, are they really buying it because they think it's a way better system than, let's say, the one that come with the car? Or are they also, the builder type that they want to contribute, like, to what you guys are doing?
I would
Or
say
is it
the
a bit of
vast
both?
majority is the former. There's definitely some people that are just excited to, to try it out and to develop and to work on it. But I think, the vast majority of our users, probably 90+%, just uses it and doesn't really do much beyond that. I think if you
Interesting.
commute a lot, it really is worth it. It makes a really big difference if you spend a decent amount of time on the highway. Yeah.
I'm curious, like, okay, maybe let's at least wrap up the papers first. So, what do you think are some future directions, like, given that one model is starting to show some signs of life, at least comparable, if not slightly better, maybe than what you had before?
Yeah, I mean, so the thing that we're working on now is, like I mentioned briefly, we switched from using kind of MPC to make recovery trajectories back to the human kind of ground truth trajectory to having a world model predict a recovery path. The second strategy is much more sensitive and requires more thought and tuning of the noise models during simulation to get the recoveries that you want. And that's something that we're kind of struggling with right now. So explicitly, one of the problems we have is that some cars have really bad controls, and those seem to suffer from this increased finickiness. And so even though the overall performance of these new strategies is better, they are more sensitive to kind of controls noise. And so that's something we're dealing with now, and that's kind of holding us back into shipping these improvements. But as soon as we've dealt with that, made the system more robust, we expect we can ship world model trained models that just understand the nuance of the scene much better, because we've currently been limited basically by the simulator artifacts. So we think that by shipping the world model things, we can remove the bottlenecks and the models will get a lot smarter, and just understand nuance better.
Yeah, I was just gonna ask, like, is it? I'm trying to get a sense on. Okay, let's say you created a world model using a certain data set, and I suppose to build a model that is trained using world model, is it like how much can you get the juice out of one single world model? Like, is it like, because a world model can, in theory, simulate nearly an infinite, like, scenarios, right? But so what I'm trying to ask is, would the compute be better spent, maybe training a bigger world model on a bigger data set, or just, okay, fix this world model and then just run more simulation with this world model?
I see, yeah. You're saying kind of, in terms of the world model, do we spend more time training the world model or inference of the world model?
Exactly. Yeah. At which point do you feel that, like, because you need I mean, everyone has a finite budget, right? Compute budget, even NVIDIA.
Yeah. So I could just tell you what we're doing now, but right now we spend quite a bit more compute training the world models. But that's also because the policy models that we're training in simulation are still very, very small. Like, they're on the order of a few megabytes. They have very little flops. So it's not something like we're kind of been dealing with other problems. So when we do scale that, it's not clear how that will scale. But at least for order of magnitude, it's 50-50 right now.
Got it. But you imagine maybe more will be at inference as your world model become better, and then you just use that checkpoint of that world model a lot more to generate a lot more.
It's hard to say though, because these kind of transformer models, like the world model, they really scale well with compute. I mean, that's obviously true for LLMs, but that's also been our experience. Every time we scale the compute, we scale the data set, we just see that the world model is just better, like produces higher quality stuff.
Got it. So I guess so I mean, it sounds like, I mean, at least on this paper, you guys have not even like make the full use of all the video data set that you guys have at your disposal. When you finally have to compute, is that the intention to take the full thing that you guys have? Like,
but yeah, I mean, we use as much data as is practical and useful right now. It's just currently we have some other bottlenecks, but we've been starting to pull in much more data to kind of prepare for this. I mean, we've been pulling in a few gigabit of data from our fleet basically consistently for 6 months, and we kind of expect to continue that. We'll have, we have data sets that are now a few million minutes of driving. We can probably scale that to a few tens. I mean, maybe 20 million minutes of driving. But other things have to get better too for that to translate into improvements.
Got it. And do you guys actually make a distinction between when, like, the data that's being collected, when it's like when it's like the whole entire drive, whether it's engaged or disengaged, you focus a lot more on the segments where the human kind of take over and go from engaged to disengaged?
So currently all the base models are trained on everything, and the policy models is only taught to mimic the human driving. So we explicitly exclude everything where OpenPilot was engaged. So we only try to mimic the actual human driving, and we currently don't do any other filtering in terms of like looking for interesting segments or complicated segments or anything like that. That's something we just kind of started looking into, but so far we've never done that.
Got it. Yeah. I mean, I'm just trying to think, like, I don't know whether it's the right intuition, but I imagine the the highest signal to noise is perhaps when the human decided, okay, the AI is not good enough, I want to take over. But what you're saying is that right now you don't think about those juncture. You just, so long it's disengaged, you take it.
I mean, I think they're kind of two different philosophies that both work. I mean, there's quite a few self-driving labs that basically see the only ground truth for recovery as exactly what you're saying. At the point that a human takes over, we know a recovery is starting, and that recovery lasts for some period of time. And I think that is a valid way to get recoveries, and is a way that you can get recoveries without simulation at all. What we're doing is kind of completely different because we're introducing deviations and then telling it to correct from the introduced deviations. I think there are two valid methods to generate recovery trajectories to train on. Probably in the future, we will use both to some extent. But right now, we fully focused on this simulated deviation and recovery, and we know there's way, way more we can do with this strategy. So we're not really spending much time on the other side.
Got it.
But yeah, I think it's a completely valid way. I mean, many labs have done this and with quite some success. And I think that works even to some extent entirely off policy, because you are basically guaranteed that when the human takes over, they're starting at least some level of recovery.
Got it. Yeah. Yeah, but anyway, I mean, thank you so much for sharing your work.
Thank
I
you.
think increasingly, yeah, a lot of these are very, very close source. So it's rare to have something like this on open. But maybe, along that same line, like I wonder if you can share your view on, I mean, not that many people are doing end to end. I guess Tesla is one. I think Wave is probably also doing something similar. How do you think Comma approach is different? Obviously, your ethos are different. You open source a lot of things. But beyond that, is there anything that you think Comma is doing a bit differently, and what are some philosophy behind it?
I mean, I think there's a lot of overlap in our strategies. I think probably the biggest difference is that we really try to stay grounded in what ML innovations can make people's experience using, our product better, in terms that they like using it more, that more people are inclined to buy it. Even though, we have some long-term goals of we want to make kind of end-to-end robotic solutions, what drives our more short-term goals is very much, what leads to improvements that translates into a good experience for people, which is why we're not really very interested in, some stuff that other companies focus on, like 90-degree turns and complicated maneuvers like parking and U-turns. I think there's a lot of value still to be extracted in terms of just autopilot level functionality that you can get by having smarter models that were trained with modern machine learning strategies, like on policy and simulation. And even with RL, I think RL innovations can make a better ADAS product. I think people get too easily distracted to have something that drives you from point A to point B, but I think there's a lot of usefulness you can get out of intelligence, even when you're just building a co-pilot / autopilot type system.
Yeah, and I mean, it sounds like if going to your earlier point about the users, like majority of users are doing it not because they're geeks, they just think it's a better product. And you guys are open source a lot of your stack. How receptive are some of these car makers to actually just adopting OpenPilot?
I mean, no normal car maker has adopted OpenPilot as far as I know. There's
so they're abnormal ones.
I mean, there's startups and stuff that I think are more interested in this, and that have I don't know if they'll make it or not, but they're definitely more interested in this, and I think it's a good idea. I mean, I think it's always a good idea to start with OpenPilot, even if you think you can replace parts with some better in-house stack. Obviously we have a system that works pretty well, so I think it's a good place for people to start. But we haven't really had any interest in working with car manufacturers. They have limitations and constraints that kind of don't fit well with our company. We just want to make the best research progress possible while also making money shipping a product. And working with car manufacturers kind of gets in the way of some of those things, unfortunately.
Got it. Yeah, they have usually completely non-technical consideration. Yeah, but anyway, I mean, first of all, thank you so much for your time, and more importantly, thank you for even writing this paper. I mean, I myself have been like kind of tracking what you guys have been doing, over the years. And yeah, you guys suddenly show up with a paper, oh, okay, that's great.
Yeah, thank you. Appreciate it.
Yeah. Hopefully, when you guys do another like big work again, it would be great if you guys can like summarize it in some paper, and then we can
Yeah.
get you on again. to
Sounds
chat
good.
more.
Yeah, unfortunately, we don't have much time for things like papers, but I'm really glad we put in the effort for this one. I think it's captures pretty well what we've been working on for a while. So
Yeah, I absolutely. I think it takes so much effort to when you're trying to ship fast and you have a real product, you have like paying customers. So obviously you need to take care of those first, and then put in the time to put in a paper like this. I think is really commendable. So yeah. Anyway, thank you.
Thank you. Yeah, thank you for having me on.
Yeah, honestly, I just wish more people read this paper. So hopefully, I don't know, like this is not that many people listen to our podcast, but a lot of researchers do. So hopefully, some researchers, get some inspiration from your work.
No, I'm excited to get it out there. I mean, as far as I know, it's the first kind of example of something this end-to-end being deployed in the real world. So we're pretty excited about that.
Yeah, deploy in the real world. That's the key. Deploy in the real world. Yeah, not in simulation. Okay, well, thank you so much, Arrow. Really appreciate your time, man.
And have a good rest of your day.